So let's finish the last part of entropy. We're talking about union-closed conjecture, trying to prove that for union-closed family. So let's quickly recall. The union-closed family is the family that for every two members in the family, their union, the set, also lies in the family. So there is a conjecture saying that for every such family, there exists an element that lies in at least half of the members of F. And previously, there's no, it's not even known that there exists an element that lies in 1% of the members in the union-closed family. And the recent development is now we know, instead of 1/2, we know a positive fraction, in particular, this 0.38 proportion of sets containing a particular element in the ground sets. The proof goes by, we make use of some analytic lemma about properties of this binary entropy function. This is rather technical, so we skip it. We assume it's a black box. Then we prove the theorem assuming claim 2. This is the thing we haven't finished proving, so we're going to do that today. This claim is saying if we take two independent random sets, subset of n, or in other words, look at their characteristic function, take two independent random length n binary vector. We don't know their distribution. We just know that they are independent of each other. And assume that there's, for any coordinates, any elements in the ground set I, the probability that I does not lie in the set, or AI equal to 0, is at least P. The same holds for BI. Then we have a lower bound on the entropy of the union of these two sets. So now I'm interchanging this A union B notation for both the set notation, if you think of A as a subset of n, or in terms of the characteristic function. And we can lower bound it by this number, some constant, times the sum of the entropy of each one of them. Assuming this, well, the theorem then follows quickly. Let's quickly go through this part. We can define this P, which locates the most popular element. So what is this P? This is the minimum over all I, such that this is the probabilistic term. Basically, in the counting term, is saying the proportion of sets A that does not contain this I. So you take the minimum such I that the proportion of A does not contain I. 1 minus P then, by definition, will be the most popular I that lies in the largest proportion of members of F. So our goal is to lower bound this 1 minus P. Okay, and the proof is now simple. We sample independent and uniformly two copies of sets in F, A and B. Then by maximality, we know their entropy is log of the cardinality of F. Then by claim 2, well, we can now apply claim 2 because how we define P make sure that this is true just by definition. So we have the entropy of the union of these two sets is at least P over 2 phi times the sum of these two entropy, which is 2 times log F. Then we get a lower bound on this entropy of A union B. Now the key observation is that A union B itself is a set in F by the union closed property of F. What does that mean? That means this is a random set sampled taking value from this family F. I don't know its distribution, but I do know by maximality, this entropy of this random set, A union B, is at most log of cardinality of F. Putting these two bounds together, then we get the lower bound on 1 minus P, the desired 38% proportion. Okay. So 2 days ago, we stopped here. Let's continue from here to finish the entropy parts. Let me copy this. Okay, so let's recall claim 2, saying that we have two random subset of n, two random binary vectors, binary vector. We don't know their distribution. We just know that they are independent, and we assume that no element, for every element, it's missing the AI equal to 0 and BI equal to 0, the probability is lower bounded by P. And our goal is to lower bound the entropy of the union of these two sets. So look at this union of these two sets. This itself is a subset of n. So we can look at its coordinates, every coordinate I from 0 to n, and use chain rule to expand it using its coordinates. So by chain rule, its entropy is the sum over all coordinates I. The entropy, the information we get from the ith coordinates of A union B, the characteristic vector of A union B, given all the previous bits. This means all the coordinates that's before I, coordinate I. Now, since this, all the previous bits of A union B is determined by all the previous bits of A and all the previous bits of B, this information is larger than this. This is determined by this one. So when you condition on something that has larger information, the additional entropy goes, the conditional entropy can only drop. So we have greater or equal to this value. Okay, no problem. So once again, entropy of A union B, that's the thing we want to bound from below, is at least this quantity now. Now we define this Px. What is Px? So we want to break these two up. Okay, so let's consider this Px, which is the probability that AI equal to 0 conditioned on all the previous bits, the prefix of A in the first I minus 1 coordinate equals to x. Then what is the condition on these? What's the probability that the ith bit is 0? Similarly, Qy is the conditional probability that the previous bits of B is y. Then what is the probability that the ith bit is 0? By definition, if we take expectation over all possible previous bits, the prefix of Px, if you take expectation over this, right, then this, you just recover the probability of AI equal to 0. Similarly, for the other one, expectation of y, Qy over y is probability that Pi equal to 0. Another thing, slightly less obvious, but still follows from definition, is if we take expectation not over P of X, but over this binary entropy function of P of X. What is this quantity? So let's write it out. This is the expectation of X over X, H, and what's inside? Let's just write out its definition. Now we claim that this equals to basically just the conditional entropy of AI, the ith bit of A, conditioning on the previous bits of A. This is because, let's write down this definition. This conditional probability definition is entropy of AI conditioned on the previous bit being some assignments. And we're taking expectation over this different conditioning value, right? This is the definition. Now, if you compare these two, this guy and this guy are the same because AI is basically a Bernoulli random variable taking value 0 or 1 with certain probability little p, with probability little p, certain p taking value 0 and otherwise taking 1, which is precisely this guy. This is the probability it takes 0, right? This little p here. And this little entropy function is the binary entropy function is by definition, recording the entropy of a Bernoulli random variable. Okay, so similarly, we have this. Now, with this auxiliary thing defined, we can go back to this term to continue. So now we can write, let's look at this one term. In the sum. So we have entropy of the union of the sets is at least sum over all I, this term. So look at this one term. Now we have, this is where we're going to use claim 1. So this by definition is equals to this term h of px qy. This is by definition. This is again because this is a Bernoulli random variable taking value 0 or 1 with certain probability. Okay, and since AI, BI are independent, A and B are independent, so when you assign some value, X and Y, oh, I made a mistake here. I should say this equals to X, this equals to Y, and this probability, conditional probability. So we are not actually looking this term, but we're looking this term where the conditioning takes, we actually assign the value, is this guy, right? Since A and B are independent, this is a Bernoulli random variable taking value 0 with probability px times qy by definition. Because this is 0 if and only if AI and BI are both 0. If one of them is 1, the union will contain element I. It becomes 0. Let me write it down. This equals 0 if and only if AI equal to 0 and BI equal to 0. Okay. And here we use the fact that A and B are independent. All right. Now, now we can use claim 1. Let's recall claim 1. Claim 1 says, okay, if you have entropy or product of two things, binary entropy function of product of two numbers, then you can break up these two numbers. Write it as some constant times x hy plus y hx. So we're going to do that. That's exactly what we have here. A little binary entropy function of two numbers. These are two numbers. Okay, so we break it up into. So this thing, let's copy it down. Now this is at least by claim 1 over 2 phi times p of x h of q of y plus q of y times h of p of x. But we know what's this term, right? This term, after taking the expectation, they look fairly nice. So that's what we're going to do. We're going to take expectation, do averaging. Taking expectation, we have averaging we get, so left-hand side, expectation of left-hand side over all possible value of x and y, we get rid of this, right? It's the conditional entropy of A union B, the i's coordinate. Let me write it down. So left-hand side, we have expectation of H A union B I equals to okay. The right-hand side, again, we use independence of x and y. Independence of A and B, when you take expectation, these two are both random variable. Okay, let's recall what's qx, qypx. This is random variable. A, B are independent, so when you take the expectation, we can move the expectation inside to each term. Since A and B are independent, we have the expectation of the right-hand side equals to 1 over 2 phi. Let's move expectation over into the constant. And then what's inside, move expectation into each term, px expectation h qy plus expectation qy times expectation h px. Okay. Now we know what each one of these, what it is. Expectation of px is probability ai equals 0, qy is bi equals 0, entropy of px expectation is this guy and this guy. Plug it in, we have this equals to 1 over 2 phi probability that AI equals to 0 times the entropy that BI of BI, where we're conditioned on the previous bits, plus, this is symmetric, we have the other side, times entropy of AI conditioned on previous bits. Okay. Now we can use our hypothesis that for every I, this and this is at least P, right? So we have this is at least, move a P outside, we have P over 2 phi. And what's inside is H of AI, AI less than I, plus H of BI, BI, B less than I. Okay, so we have left-hand side bigger than right-hand side. So left-hand side, the expectation is this one. Let's move it here. So we have H of A union B I is at least this. Okay. Now we are done. You're summing over all I. What do we have? Remember, the union, what we want to prove is this lower bound. Yeah. And this guy that we want to bound from below is at least the sum over all I. This term we are trying, the whole time we are bounding the left-hand side below. So we have summing over all I, and by chain rule, we have entropy of the union is at least sum I over n. This is what we proved previously. Is at least P over 2 phi. Now, sum over all I, this guy is nothing but entropy of A by chain rule. This guy is entropy of B by chain rule. We get exactly what we want. Okay. Any question? So that concludes entropy part. The next part next method we study is the container method. So the container method, its original form, the graph container, was already out in the 80s. So the graph container, this is the part we're going to start with. Graph container, it was out already in the 80s by Kleitman and Winston, and also independently by Shapozenko. independently by Shapozenko. And later, in the past, about 10 years ago, there's a far-reaching generalization of this graph container to the so-called hypergraph container. Hypergraph container methods. This is about 10 years ago, around 2014. Let me just say 2010s. This is by two group of people, Pollock, Morris, Samoti, and independently I should use this. And independently Sexton and Thomason. So this method, hypergraph container, is considered as one of the biggest breakthroughs in the past 10 years. It has many applications. We're going to start with seeing some applications in counting problems. One of its a type of problem that's quite natural. So let's start with looking at these questions. So what is this counting problem? It's a very natural problem. So let's start with the counting problem. Basically, we deal with extremal problem, like the extremal number of a graph in Erdős-Stone-Shumovich. So this extremal type problem is saying we have a parameter, in this case, the number of edges in the graph. And we want to maximize the number of edges over some restricted family, the family of, say, triangle-free graphs or the family of H-free graphs. This is the extremal problem. After doing that, you can ask also the corresponding counting problem. So we now know that the maximum size of a triangle-free graph is n squared over 4, the number of edges. Now the next question is, how many triangle-free graphs labeled on the vertex of 1 to n are there? This is the counting problem. So counting problem, we have originally this extremal problem, which, for example, in Mantel, we know that for every n vertex triangle free graph, then the number of edges is at most n squared over 4, which is optimal by complete bipartite graph balanced. Now, the next natural question is, how many triangle-free graphs on the vertex set n? And what this means is that we are considered labeled graphs. What it means is, if we have 1, 2, 3, this is a triangle-free graph on 3 vertices, we consider it as a different graph than this one, 1, 2, 3. Although they are both isomorphic to path of length 2, but in terms of labeled graphs, they are different. The middle vertex here is 1, the middle vertex here is 2, right? So we are counting graphs up to the labeling. Any question? This is because if we don't count with labeling, then there are lots of symmetries, the graph automorphisms. The problem becomes harder. Okay, so how many triangle-free graphs on the vertex at n are there? How many? Okay. We can get a very easy lower bound. The easy lower bound is, well, okay, here in this problem, the maximum n squared over 4 is realized by, we have n over 2 vertices on each side and put all the edges in between. This has n squared over 4 edges. A key observation is that if you have a triangle-free graph, any subgraph of a triangle-free graph is also triangle-free. Okay? Since subgraphs of triangle-free graphs are also triangle-free, we can generate many triangle-free graphs by taking subgraph of, for example, the largest one. This will imply that by taking all subgraphs of complete bipartite graph, which has n squared over 4 edges, we get there are at least 2 to the n squared over 4 triangle-free graphs on vertex at n. Okay, a lot of these might be isomorphic to each other, but we are talking about labeled version. All right. Any question? So what we will see is that this easy lower bound is not very far from the truth, meaning we can prove upper bound of 2 to the n squared over 4 times a plus little o n squared. So in the power, n squared over 4 is asymptotically optimal. We should see this trivial lower bound is quite good. Okay, we will should prove an upper bound that's 2 to the n squared over 4, 1 plus little o 1. So asymptotically, we can determine the logarithm of this number. Okay. So this is the type of question we're going to study. And this counting problem, you can ask, whenever you have an extremal problem, you can ask the corresponding counting problem. Let me give another example. So here, this is example 1. The second example, what's another classical extremal result? Erdős-Corrado. So let's recall Erdős-Corrado. So in Erdős-Corrado, we given an intersecting family, a uniform intersecting family, and Erdős-Corrado gives an upper bound on the size of such family. He says that for every k uniform intersecting hypergraph, on vertex n, where for any n at least 2k, we have these, right? For any n at least 2k, and for any k uniform intersecting hypergraph on n, has size at most n minus 1, choose k minus 1. Here, the optimal construction is you take all sets containing a fixed elements. N minus 1 choose k minus 1. We can again ask the counting problem question. How many k uniform intersecting families intersecting hypergraphs or families, whatever, on vertex n, again labeled. Let's do a similar trivial bound, lower bound as above. Again, all intersecting family, its subfamily or hypergraph is subhypergraph is still intersecting. Well, since subhypergraph of an intersecting hypergraph are also intersecting, by taking all possible subfamily of this family, we get the number of intersecting family is at least 2 to the n minus 1, choose k minus 1. Okay, and we should see that this is again not bad. We will prove an upper bound that's 2 to the 1 plus little 1 times n minus 1, choose k minus 1. Okay. This is where we're going to see the first couple of applications of container theorem, container method. The counting problem. So if there's no question, we're gonna start with the graph container lemma by Kleinman and Winston. Okay. Kleinman and Winston's graph container theorem, it states the following. So we have a graph G on m vertices. And then we have some parameters. We have capital R and little q, they are natural numbers, and a real number, beta, between 0 and 1, such that we have the following inequality. So let me write it like this. 1 minus beta q times n. We require this to be at most r. This is the first inequality. But usually it's easier to verify. We know this is always less than e to the negative beta q. So this one is easier to verify, right? Most of the time we will use this. Maybe I should put parentheses here. Okay. What's enough is this hypothesis, but a strong hypothesis like this one is easier to verify. So, all right. So if inequality 1 holds, and suppose this parameter satisfies this, and suppose the graph G is locally dense. Suppose, what does it mean locally dense? For every subset of vertices S, of size at least R, as long as it's large. So this is the locally denseness. Locally denseness, so local denseness. Locally denseness. For every S of size at least R, the number of edges induced on S is at least beta S choose 2. So edge density is at least beta. This is a locally denseness for every such set. So this is the graph G. Every part, if you take a set of size at least R, you will see beta fraction of the edges. Every part, anywhere. So locally denseness. If this is true, then this is the hypothesis. Conclusion is then there exists a collection of so-called containers which is a subset of vertices Ci this is vertex set of G, where I goes from 1 to n choose q, such that first of all, each container, each Ci is not so big, at most R plus Q. Second of all, every independent, this is why it's called container, every independent set in G is contained in one of these Ci container. Okay. In particular, what it implies is that the number of independent sets of certain size, let's say n, which is at least q, is at most n choose q, r choose m minus q. Okay, so this is the statement. Oh, I wrote the whole page. Okay, here. So the theorem. Some key things here to remember is in the hypothesis, we have a graph. There is some parameter. Okay, parameter has to satisfy something. What's more important is this graph has this locally denseness condition, locally dense. As long as the graph is locally dense, then we can find a small collection, a collection of few containers to contain all independent sets as a subset. Furthermore, each such container is not so big in terms of its cardinality when you define R and Q properly. So if you have a stronger locally dense condition, meaning that R is smaller, you have a stronger control on the size of each container, CI. And the in particular part follows directly from the previous conclusion. Why? Look at every independent set of size M. Well, we know, okay, it follows actually from the proof. Very roughly speaking, we found for every independent set I, we found some fingerprint of size Q. And the choice of this fingerprint is capital N choose Q. There's no restriction on Q vertices. The N is total number of vertices, right? So this is the number of ways to choose a set of Q vertices, no restriction. After choosing that, we can then narrow down the remaining part of the independent set to a small set of size R. And then for the remaining of these independent sets, M minus Q vertices, we just choose from these remaining sets size R. The idea, so we're going to prove this. Let me write down, roughly speaking, what I just said. He states that if a graph G is locally dense, then there is a small collection of containers for its independent sets. The idea of the proof is that we can use locally dense condition of G to find fingerprint for each fingerprint, some sort of signature or inside each independent set. We can find a small set of vertices to identify, which can uniquely identify this, not uniquely, sort of group them independent set up. So let me write it down. We can group independent sets using small fingerprints. This will be the set. This fingerprint will be the set S in the proof later. So you can pay attention to the proof. And the set capital S will be the fingerprint. Now, to give this proof, we need the definition of a max degree ordering. By the name, it's very simple. Max degree ordering just means we're going to order the vertices by degree. Whose degree is larger, it comes first. That's it. Given a graph G, and given a set of vertices, so we're not just doing max degree ordering for the whole graph. We do it for every subset of vertices. We can do this ordering. So for every subset of vertices, let's just pick arbitrary one A. The max degree ordering of A is, let's say, V1, V2, to VA, such that every vertex has the largest degree in the remaining bits, such that for each I less than A, VI is a maximum degree vertex. In so VI is here in the middle, right? So if you forget about all the previous vertices, in the remaining part, VI has the largest degree inside the remaining part. So in the remaining part, that means in the graph induced by A, but with all the vertices before VI removed. Any questions about the definition? With this vertex ordering, max degree ordering defined, we can now give a proof of Kleiman and Winston's graph container. Before the formal proof, let me draw some pictures and show you the idea of the proof. Where does this requirement 1 minus beta to the q times n less than equal to r coming from, and where we use locally denseness, and how we're going to build this container, right? So here's a picture. As I said, for each, now here's the idea. We first fix independence at I. Okay, now what we're gonna do is we're gonna list the vertices in terms of max degree ordering. We list the vertices. max degree ordering. Now we're going to go through this list from left to right, from the maximum degree vertex to largest one to the rest, one by one, and try to pick out vertices in I, in this independent set I. Okay, now we say, okay, is the first vertex in the independent set I? No. Then we cross it out, not in I. Second one, no, cross it out, not in I. The third one, yes, it's in I. So let's mark it. This is in I. If this is in I, we're going to put it into a set we call S. Putting S means selected. So by doing this, we always select vertices. So vertices in capital S, the selected one is always a subset of S, I. We maintain S is a subset of I, right? Now, after we pick the first vertex, I, we need to look at its neighbors. The first vertex has some neighbor here somewhere. Maybe this is its neighbor. Since we are identifying vertices in independent sets, if this vertex is in an independent set, none of its neighbors can be in independent sets. So after picking out the first vertex, we also need to cross out all the vertices in its neighborhood. Does it make sense? This will finish one iteration of the algorithm. Now, in the second iteration, we look at remaining vertices. We have to redo this max degree ordering. Okay, but for simpleness, let's assume this is again the ordering in the picture. We're going to go over the list again and try to identify the second vertex in I. Let's say this is the second one. Let me pick one more. This is the second one in I. We again put it into this set S. Okay. Now remember, we are picking out independent sets. So its neighbor, let me use a different color. Maybe here, its neighbor must also be eliminated. So cross this out and keep going. Now, at the end, we have a set, a remaining one, available ones. So this is, if this is the remaining one, this is the remaining set. We call it A, available set A. What do we know? We know that by our construction, I always contain S, and the remaining vertices of I minus S, is always a subset of A, right? Because whatever we kicked out are those definitely not lying in I. So all the remaining one must be in A. So we have S in I minus S is in A. What does it mean? This implies I is a subset of S union A. Okay, so this is what we mean fingerprint. Fingerprint means S is a small set of vertices that can identify a larger set which contains our independent set I. A crucial observation here is that the remaining set A does not depend on I. It only depends on S. Okay, once again, even though we fix independent set I at the beginning, now in this whole process, what really matters for identifying A is what vertices we picked out. Although these vertices is depending on I, but we know it by S. When S is given, we know how exactly each iteration of this algorithm looks like. We know exactly after a certain number of steps how A looks like. So A depends only on S, not on I. This is important. So what that means is that if you have two independent sets I and I prime, where at the beginning your S picked out are the same S, then their remaining set A are the same set A. This is what we mean by grouping independences up using small fingerprints. So if two I and I prime has the same S, they're going to group up into the same pair S and A. i.e., if two distinct independent sets I and I prime have the same fingerprint S, they will be put into the same group. Group up together corresponding to S and A. This group, right? A depends on S. A depends on S. This is one container. You can think of this as a container containing I. So since there are few choices of S, we have few containers. All right. So this is, first of all, how we're going to generate containers by picture, proof by picture. Second of all, so this is a container. Containing I and containing I prime, right? So independent sets are grouped together by different containers. They are in one of these containers. So the key thing is that this fingerprint is small, so we can efficiently identify S, which then identify A. So the number of fingerprints is small. And why containers, its size is not too big. In this conclusion, we require the size of each container is not too big. This is because the locally denseness condition. Locally denseness condition is saying whenever the remaining set A is large, of size larger than R, what do we know? For every set of size larger than R, the edge density is at least beta. That means there exists a vertex as long as remaining set is large, that's linked to at least beta proportion of the vertices. So whenever you pick out the vertex, the next vertex in I, and put it in S, you shrink the available sets by 1 minus beta factor. It's a geometric factor that's shrinking very fast. Okay? This is this 1 minus beta. We carry out Q steps. All right. So all this is just informal proof sketch. We're going to write the formal proof later. It's important to keep this picture in mind, how this algorithm goes, right? So let me write down the last bit. The locally denseness is make sure that pick a vertex V. Okay. As we delete. Any question about the idea? Now let's carry out this proof rigorously. I think it's good to have this picture. So let me draw this. Proof of the Kleiman-Winston. Let I be an independent set in G run the following algorithm. So this algorithm why I didn't? Oh, okay. Okay. So here's the algorithm. We input the graph G and input the independent set I of this graph, some independent sets. And initially, we set the set of available vertices, the active sets A, to be the whole set of vertices, V of G. So A stands for, A is the active set. And S is the empty set, and X stands for the selective, the set of selective ones, selective vertices of, and this is the fingerprint of I. So S is a subset of I we will maintain. Okay. So for the ith iteration, this is the beginning. For the ith iteration, I goes from 1 to to Q. We do the following. Do two steps. Step 1, we select the next vertex in I. What it means is that we're going to take the max degree ordering of A. Let's say it's V1, V2, VA. Now we're gonna we pick out, in this ordering, we pick out the first vertex in the ordering. Let VTI be the first, which means the minimal index vertex in I. And then we're going to move VTI, this vertex, from A to the set S, the selective vertices. Okay. Step 2, we're going to update A. So remember, we pick out the first vertex here. Now update A means we're going to delete the neighborhoods of these selective vertices. So we're going to delete So first of all, we delete all vertices previous to this first selective vertex. This is the first. Let me put the picture here. Okay. Remember, let's say this is VTI. This is the beginning of the I step. We pick out VTI. We need to delete all the vertices before it. This is this. And we're going to delete the neighborhoods of VTI intersecting A. We delete all these vertices from A. This is this bit we delete, right? Now let's say we finish the first round. This is the current round, second round. We go through, we pick out the first vertex in I, we delete all the vertices before it. This is this part. We delete its neighbors. So this is this part that we delete. Okay. At the end, we output the output is you have set S, the selective ones. It comes in order VT1, VT2, VTQ, Q steps, we run it, and the remaining set of active vertices A. This is the algorithm. Okay. Not very pretty. Good. So here's the algorithm. Any questions about the algorithm? Okay. Now we're going to list some properties of this algorithm. There's a claim. The claim is after these Q steps, after we select this S, the final set of active vertices A is not too large. Final A is not large. In particular, A is going to be smaller than R. Strictly smaller than R. Less equal or less, doesn't matter. Smaller than R. Assuming the claim, we're going to finish the proof. All right. So let's assume the claim. Claim implies the theorem. Why? Well, let's have a few observations. By our algorithm, we always choose vertices in I to put in S. So we maintain S is a subset of I. This is obvious. And by our algorithm, we always kick out vertices not in I. So the remaining of the vertices of I lies in A. We mentioned this in the sketch. Now, from this algorithm, it should be clear. So what do we have? I is a, what did I do? Subset of S union A. Second of all, the key thing is the final A as I said, depends only on S, not on I. Let me explain this one more time. Although for this algorithm, at the beginning, we do have an input I, and we select this set S, right? This algorithm. But think about it. If I now tell you what S is, I tell you what exactly are this VTI, VT2, VTQ. I claim that we can recover what A is without knowing I. Simply because at the beginning, we list all the vertices, which is the initial stage of A, in max degree ordering. Now, we look at the first vertex that's in S. S are the selected one, right? The first vertex in S. Then we kick out its neighborhoods in the remaining vertices. Now, for the remaining one, we do the same. We list it in terms of max degree ordering. We pick out the first vertex in S, kick out its neighborhood. Keep doing this for all vertices in S. Then the remaining set A will be identified. It has nothing to do with I. Although we use I to generate S, but if we give an S, A is determined. Is this clear? This is the key part. If this part is not clear, please ask. Good. Now, how do we finish the proof? Well, then, as I said, we're just going to let C, our container, to be S union A, which then will contain the independent set I. And the size of this container is at most size of S plus size of A. actually equals to S and A. And S is of size Q. We pick out Q vertices in S. We run Q steps. And A, by the claim, is size at most R. So it's at most Q plus R. And let me emphasize that A depends only on S. Okay, S union A of S. Let's recall our conclusion. What's the conclusion we have to prove? Well, we have a collection of containers of size R plus Q. We proved it. You need to prove that the number of containers is not so small. Number of containers is small. And area independence is contained in some container. So both these two are done. We have C from different, this is choice of S, right? This is A. S is of size Q, A is of size at most R. This is because once we determine S, A is determined. So S, C container depends again on S. So the number of choices for S is exactly N choose Q because S is of size Q. Done. And why is this done? This is again the number of choices to pick out S. And if your container, if your independence is of size M, the remaining M minus Q vertices must lie in A, which is of size R. Done. Let's write it out. Okay. C also, this container also depends only on S. A depends on S, C equals to S union AS. So C depends only on S. This means the number of containers equals to the number of choice of the number of containers C equals to the number of fingerprints. Is at most actually number of fingerprints S. C depends on S. And S is at most. S is of size at most Q, right? So it's at most N choose Q. This is because S is of size Q. Good. And the number of independent sets M is at most. Well, we first pick its fingerprint, which is N choose Q S, and the remaining set pick the fingerprint S, and the remaining set we have I minus S is in A. Subs A is of size at most R. So this is R choose M minus Q. So I think it's about time. I will prove this claim next time. The claim is also not very hard. Let me quickly say why the claim is true, and then we run the details next time. A must be small because if A is large, larger than R, then remember, locally denseness means that whenever you have a set here A, if it's bigger than R after Q steps, then every time we can pick out the vertex which has at least beta proportion of neighbors in A. So we pick out this next vertex in I in step 1. In step 2, we're going to kill beta proportion of vertices when we remove these. So every time we shrink by a 1 minus beta fraction. But if you shrink by a 1 minus beta fraction, you do it q times, we shrink 1 minus beta to the q this much after q iterations times n, this is going to be less than r. This is the proof, basically. All right? Any question? And then if there's no question, we're going to continue next week. All right? Thanks for listening.